Hello, and welcome to our May edition of the Micron MVP webinar series. I'm your host, Matt Wokus, and today with me is one of our returning champions, Doug Rollins, a senior technical marketing engineer and frequent blogger at Micron.com. And this month, we're going to be talking about the end of Windows Server 2003 and the beginning of the Flash revolution. So, Doug, how you doing?
Couldn't be better, thanks.
Good. So, tell us what's going on with Windows 2003.
Well, what do you say we jump right in?
Okay.
So, first of all, thanks everybody for your time. Appreciate your attendance. Appreciate your taking some time out of your day to sit with us and talk a little bit about what's happening with Server 2003, and we'll take a look at what some of the paths forward are beyond Server 2003, and let's get started. So if we wind the clock back several years, and I'm actually old enough to remember this very well, Server 2003 was released way back in April of 2003. And the times were different. Everything was really different back then. If we take a look, for example, at hard drives were, relatively speaking, small. We measured hard drive capacity in a handful of gigabytes. SSDs were really new. There was probably one or maybe two manufacturers, mostly specialty products, and we measured those in a very, very, very small handful of gigabytes, and they were incredibly expensive, no matter how you looked at them. Virtualization, one could argue virtualization was just a rehash of the old mainframe days, but virtualization as a broadly adopted IT strategy or IT solution was really in its infancy back in 2003. Power management, especially if you look at server power management, we really didn't think so much about power back then. Power management itself was rudimentary if it existed at all. Processors, the architecture was 32-bit, period, end of story. In our servers, we had 32-bit CPUs, one or two of them, and maybe we had 4 sockets. And those processors, they didn't have a whole lot of horsepower back in April of 2003. The norm was single core, and the front side bus was relatively slow at 133 megahertz. We hadn't really thought of QPI yet, so that hadn't come along. So that's sort of a picture of what things looked like back in the day when Server 2003 was first introduced. And times do change. Now we look at hard drives, and they're really measured in a handful of terabytes, not a handful of gigabytes. SSDs, well, they're still a little bit smaller, but it's a very, very large handful of gigabytes that we measure them in. And cost-wise, no matter how you slice and dice the cost, whether it's cost per gigabyte or whether it's cost for performance, cost per useful work performed, in all cases, the cost has gone down dramatically to where they've become mainstream as well. Virtualization, standard practice in IT shops, and not just the really big ones. Server power management. We think more about power management across the enterprise now, but especially server power management inside the platform is extremely mature, and it's now become just a standard feature. And likewise on CPUs, multiple cores, multiple threads. Clearly we still have multiple sockets. We've stepped away from the concept of the front side bus and moved to quick path interconnect. So again, much better performance. But at the end of the day, the landscape within IT has changed dramatically. Inside the platform, the things that are mainstream have also changed dramatically. And our operating system is going to need to change dramatically too. Server 2003 has reached end of life. Microsoft's official end of support is going to be July 14th of 2015. So,
and that's
sorry, go ahead.
I'm sorry to interrupt there, but yeah, so it does seem to me that the architecture, the actual just infrastructure, has really gotten a lot more complex between 2013 or 2003 and today.
Well, it has. I mean, in those ensuing 12 years, a lot's changed, but at the end of the day, there's still more than 11 million servers out there running Server 2003. These are active systems performing regular IT functions. And if we were going to upgrade all of them, we were going to either upgrade or replace them. Hewlett-Packard had an estimate that said to do that, we'd need to budget about $10 billion total. So we've kind of got a bit of an impasse here. We've got The end of support coming on July 14th. We've got $10 billion to upgrade or replace all the platforms running it, and there's 11.7 million of them out there in active duty in RIS shops. So the first question is, well, do I have to do anything? Sure, Server 2003 end of support's coming, but so what? Can I still run Server 2003? And the short answer is, yeah, you can, but there are some caveats. There's some things to be aware of if you want to do that. First of all, it's going to get expensive. It's going to get really expensive in terms of maintaining these legacy platforms. Matt, like you pointed out a minute ago, this is reaching back 12 plus years. And most of us in our IT shops maintain some sort of spares kit or spares assembly for the systems we have in active duty. So if we're talking about systems that are 10 or 12 years old, finding those spares on the open market will be extraordinarily difficult if you don't already have them stocked. And if you do find them on the open market, they're going to be extremely expensive. But perhaps a bigger concern is some of the changes in compliance requirements that have happened since Server 2003 was introduced. Specifically, we've got some very stringent requirements around security, specifically HIPAA, Sarbanes-Oxley, and a litany of other ones. And some of these requirements, they really do require that the platform that you're running the app on, which is required to comply, have some special features and some capabilities in it. Everything from encryption to either at rest or on the fly encryption, and a litany of other features are really table stakes if you're going to run these highly regulated applications in highly regulated markets on these platforms. Compliance is extremely difficult on this old hardware and old software. Support. I mean, we touched on that a couple times. Microsoft is ending support, period, end of story. What that's going to mean to us if we're still running Server 2003 is we don't get any more service packs. We don't get any more patches. There is no more Patch Tuesday for Server 2003, which on the one hand is a good thing, but longer term is really not such a good thing. Likewise, if we look at compatibility, so we have these really old legacy platforms running Server 2003, it becomes more and more difficult with each passing generation to ensure that anything new we want to attach to them in fact works. Something as simple as upgrading to a faster fiber channel HBA, for example. There may not be a driver out there at all that supports Server 2003. There may be, but there may not be. And as we get farther and farther past the Server 2003 end of support, the probability of finding those necessary components gets smaller and smaller. And then the last thing we want to look at is overall efficiency. You know, back in the day when we first had Server 2003 released, our model was really one-to-one. It was one operating system, one application, one piece of hardware. Sure, we could cluster them together. We could have multiple instances of an application that ran in a cluster mode and failed over and shared the work, but we still had one OS on one piece of hardware running one instance of an application. And of course, that's dramatically changed. I mentioned earlier that virtualization has really gone mainstream, and as part of that, the one-to-one workload to server deployments are extremely rare. They're few and far between if they exist at all. So there really are a couple options that we have as we reach the EOL of Server 2003 and as we look at the platforms it's running on and decide what it is we're going to do with them. Our first option would be to upgrade. So if our platform can take some memory and some storage components, some upgrades there, if we can get those installed and up and running, if our platform then meets the minimum requirements around Server 2012, we can add Server 2012 to it. Again, so long as the upgrade path is available and supports the minimum requirements around Server 2012, it's a good option. You'll end up saving quite a bit of money, either per system, per rack, or per data center, because by reusing what you have and adding a few upgrades, you end up saving quite a bit of money. But what if you can't? What if, Matt, what if you and I are running platforms that are so old that in fact they just can't be upgraded to meet the minimum specs for Server 2012? Well, fortunately, we have only one option left, which is really to buy new. We can replace these platforms. And what we would do then is we would probably make the jump to server 2012 as part of that overall new server purchase. But no matter which one we pick, both of these roads lead to flash or SSDs inside the system. At the end of the day, what we end up with is we get far more performance, far more value, far more measurable, useful work output done for the amount of dollars that we spend. And if you look, for example, at our line of SSDs, they really run the gamut. Everything from simple SSDs that enable quick, resilient system booting through SSDs that work great as VMDK stores and virtualization, through database acceleration, and a litany of other applications that we're going to run in our IT shops. Flash, in general, makes all of these better, faster, stronger. And in particular, if you look at our product line, because it does span the gamut, we're not really trying to put one SSD in every socket, but we have tailor-made products for each of those sockets. So whether we choose to upgrade the platforms we have or buy new, SSDs inside those platforms is a very good decision.
So it's really, Doug, what you're saying is with all the complexity and other attributes you have to look for in a system nowadays, power, performance, capacity, it really, you have to have SSDs to be able to enable all that.
That's correct. You really do. And we'll talk a little bit about why that is. I've got some data here that I'll share that makes a direct comparison between how we used to do things, which is looking at a very high-performance spin drive, versus how we really need to be doing things as we move out of the Server 2003 realm and we modernize so much of our infrastructure. And in particular, we want to look at, maybe a different concept for some of the attendees. It's the idea of measuring the value of a storage system in terms of the useful work that the storage system accomplishes. And we look at useful work as work that's directly related to something a business needs to get done. It can be anything. It can be an email system. It can be a report generation system, an analytics system. But no matter what platform and no matter what application we're running, the key here is to think about what I get out of my investment. How much useful work do I get out of my storage investment? And again, useful work is something that's relevant to the business, and we want to be able to measure that. So we can measure it for storage devices like SSDs, hard drives, arrays, or SANs. We can measure it in terms of the access rate, how quickly they can read data from the storage when the application requires it, and write data to the storage when the application needs to store it permanently. And we have a nice, convenient, standardized way of expressing this, which is simply input-output operations per second, or how many reads and writes a given storage device or technology can do in 1 second. When we're measuring useful work, it's really helpful that our friends at the Storage Networking Industry Association, or SNIA, have developed a standard method of measuring SSD performance. As most of the folks on the phone probably already realize, SSD performance tends to evolve. As one writes it, it tends to slow down from the fresh factory state. And the folks at SNIA have written a performance test specification that says exactly how to measure it so we can do head-to-head comparisons. In particular, it focuses on really these 4 key areas that are in front of us. The results have to be repeatable, reliable, and accurate. So the Performance Test Spec Enterprise really focuses on those 3 areas. The ability that if I measure it and Matt measures it, or anyone in the audience measures it according to the spec, we're all going to get exactly the same results, and that's why we're enabled to do these head-to-head comparisons. The testing is always done at the device level. Within SNIA, we ended up factoring out things like file systems. And one could argue that, well, it's not relevant without a file system, but the truth is the file system can have an effect on performance. So if we're talking about head-to-head device-to-device, we factor out the file system because it should remain relatively constant. The test spec also says what we're going to measure and how we're going to measure it. And at the end of the day, it's really about making these direct, fair comparisons between two storage devices so we can make this head-to-head decision.
And this is for storage devices, both hard drives and solid-state drives.
That is a good question. So in particular, the Performance Test Spec Enterprise IOPS test is focused on SSD performance because SSDs are unique in that their performance changes with time. What the PTSE does is it enables you to normalize that out. And in fact, by executing the PTSE according to the spec, the results you get are steady state and repeatable. So the fact that SSD performance is normally variable has already been taken care of with the method it measures performance. Now that
and
said, PTSD Performance Test Spec Enterprise. There's also a client version, which the client version isn't really interesting to this space. It is to the portable space, but in the enterprise space, it's the enterprise test that we're really focused on. But you can also apply the same thing to hard drives. Even though hard drive performance does not evolve over time, you can take this same hard drive, plug it into the same reference test platform. That's the SNIA description of the hardware system that meets the specification requirements. And you can execute a test on it in accordance with the Performance Test Spec Enterprise. So we could even compare directly a rotating drive to an SSD and ensure accurate, fair, repeatable, head-to-head device-level comparison. And in fact, it's good allude there, Matt, because we're going to do that in just a minute.
Okay.
So just wrap it up real quick on SNIA. The output is always steady state. So what we know is that the SSD performance has settled down. The numbers we're looking at are reflective of long-term use performance. The output gives us 56 separate data points. It has 7 different read-write ratios and 8 different transfer sizes. And it's also completely vendor and technology neutral, meaning the test spec has no concept of interface or memory type or firmware or over-provisioning or any of the other things that an SSD vendor may do to make their drive stand out or be different from others. It has no idea. It just sends I/O through the interface and measures the results. So it is completely agnostic. So that's how we're going to measure it. That's how we're going to measure the useful work of any of our storage devices. But we need to do that in a context. And the context would be around how long do we normally have a platform in service. We want to measure the useful work that we can accomplish during our normal platform refresh cycle. And 1 year, that's probably pretty short, but platform refresh cycles of 3 years and 5 years are pretty normal in most enterprises. Most companies will plan around either the 3 or the 5 year refresh cycle for a given platform. So the idea here is we want to look at how much we get out of a given storage type or given storage device during the time it's in service, which is that platform refresh cycle. And we'll look at 1, 3, and 5 years. So what I've got here, we were just talking about the output of SNIA's performance test spec. This is an example of output. What we've got is the performance measured for a 600 gigabyte, 15,000 RPM SAS hard drive. And in each of these cells, the output is measured in input-output operations per second, or IOPS. Along the top of each one of these charts, we have 100% write on the left and 100% read over on the right. So as we move from the left column over to the right column, the data moves from all writes to all reads. And as you can see, there's several mixes in between. There's a 5% read, a 35% read, a 50-50, and then also the other side. Similarly, the output of the performance test spec looks at different transfer sizes, starting at half a kibibyte all the way down to 1024 kibibytes with several others in the middle. So anytime we're interested in a specific performance metric, we can find the transfer size in this column, trace that horizontal row over to the read-write ratio, and get a direct output in terms of IOs per second. So what we see here is in this 56-point matrix, these are all the performance specs that are measured for this drive, and they're all measured in IOs per second. So as an example, we're going to take a look at a metric that's often used in enterprise platforms. And what I've done here is we're looking at the 65% read, 35% write, or roughly 2/3 read, 1/3 write. And if you trace over to the left horizontally, you'll see that's the 8 kilobyte transfer. So what we're looking at here is a SAS 600 gig 15K RPM hard drive, and we're looking at 8K transfers with 2/3 read, 1/3 write. And if we look at that cell in our PTS output, we see that this 600 gig 15,000 RPM hard drive is able to do, well, it's just south of 430 IOs per second. It's 429.1, but it's pretty close to 430. And since that's per second, we can do some arithmetic and do some conversion factors, and we can calculate how many we get in a year. This enables us to look at how much useful work, remember we said useful work was input-outputs on a storage device, that drive can do in 1 year. And I'll save everyone the boredom of the arithmetic. It ends up being about 13.5 billion IOs every year. So our SAS hard drive. Go ahead.
Oh no, and an 8K random block. What type of files are that type of block size?
It's a good question. So it depends. If we think about a structured query language database, typically you'll see these relatively small transfers on a system that is not memory rich. In other words, a system that's memory starved. If it doesn't have a whole lot of memory, it's not able to do a lot of predictive read ahead. It's not able to do nearly as many lazy writes. And there's other apps that support this transfer size too, with a read 2, write 1 is a common ratio. But a lot of enterprises use this metric in particular to gauge the overall performance of an SQL database. So does it map over exactly, Matt? No, probably not. But this one's a pretty common metric to take a look at that type of an application and get a sort of a finger in the air gauge to see what kind of performance we're going to get.
Mm-hmm. Okay.
And keep in mind too that I didn't mention this earlier, but the Performance Test Spec Enterprise says that when you measure performance, you're required to do it at the maximum queue depth that the device supports. So in other words, you're required to load that device up as much as possible, which tends to generate better numbers in this chart. You can optionally load it with less, but these numbers go down. Make sense?
Gotcha. That makes sense.
So what if we take a look at an SSD? So here we have the exact same test process measured on the exact same test harness, and we're looking at a Micron M500DC 480 gig. So the first thing you're going to notice is it's slightly smaller than our SAS drive, but it's the exact same outputs. We've got read-write ratio along the top, transfer size along the left. And if we focus in on the exact same metric, that 8 kilobyte read 2, write 1, we'd see that the M500DC does, well, it's just north of 22,000 input-outputs per second. So we end up, again, if we do the arithmetic, this SSD will do about 693 billion IOs in 1 year. And because we measure this in a standard mechanism, it's fair to make a direct comparison between the two. So I just pulled the data from the other slides and put them side by side so we could make this direct comparison. On the left, we've got our 600 gig 15K RPM SAS hard drive, which in 1 year does about 15.3 billion IOs. And on the right, we have our Micron M500DC 480 gig enterprise SSD. And in the same year, it does about 693 billion IOs. So there's a bit of a difference there when we compare them.
Yeah.
Now, if we take a look at, that's in 1 year. But remember, we said that our platform refresh cycle might be 3 years, it might be 5 years, it might be 1 year, but probably not. So what we can do here is look at a direct comparison by year. So we know from the prior slide, our SAS hard drive does about 15 billion IOs. And we know that our SSD does about 693 billion. That's in the first year. So in the second year, our hard drive has done about 42 billion IOs, and our SSD's done 783. So it's not double. We'll talk about that in just a sec. And then by the end of year 5, we've got 75 billion IOs done by our hard drive, and we're still at 783 for our SSD. And I want to talk about that for just a minute. You'll probably notice there's an asterisk besides each of the SSD IO numbers. And I want to call your attention to that note at the bottom right. We have to remember that SSDs wear as we write them. When we're doing this particular metric, remember 1/3 of our traffic is writes, 2/3 is reads. So that 1/3 that's writes will cause wear to the SSD. This SSD has a TBW rating, total bytes written. This is a warranted amount of data you can write through the interface before the drive goes read-only, and we'll talk about that in a minute, and we'll talk about how to monitor it, where Micron will ensure that you can write that much data through it before it goes into read-only mode. And again, sparing the audience the pain of the arithmetic, if you look at 1/3 of the total IOs being writes, 8K in size, then we look at the write rate, we can figure out that by the time, and we look at the TBW number, we figure out that we reach TBW when the drive is executed 783 billion IOs. So that's why we go flat from the 3-year, sort of that dark brownish metric, to the 5-year, the yellow metric with the SSD. We also know that hard drives, they don't wear as you write them. They have other wear characteristics and other failure modes that we can talk about at the end if we want to, but we're assuming here that the hard drive does not fail strictly due to wear. So from 1 year to 3 year to 5 years, we can just keep adding up the total number of IOs executed. But it kind of begs the question, so what is our realistic platform refresh cycle? If it's 3 years, we can expect to get about 42 billion IOs out of our hard drive. If it's 5 years, we can expect to get about 75 billion. And from our SSD, same thing applies. If it's 3 years or 5 years, we can expect to get a total of about 783 billion IOs out of that SSD.
And again, I just want to make sure I'm understanding your math correctly. So this is with this example, it's 1/3 of those IOs are writing to the SSD, and
right,
so
and writing is the only operation that causes wear.
Okay, and so like for instance, that first year it's 693, so that's what 231 billion writes of 8K bit blocks is going to have that sort of wear to the total bytes written to the SSD. Okay.
Yeah, what you can do is you can look at the IO rate from that matrix earlier. It was like 22,000-ish. Take 1/3 of that, which I can't do the arithmetic in my head, but it's about, 14, a little more than 4, sorry, 1/3 of it would be a little more than 7. Multiply it by 8K, and that tells you how much data you write per second. Look at the TBW number on the SSD, do the division. That'll tell you how long it'll last before it goes into read-only mode. And so again, this really just drives the point home that Matt was making. SSDs do have a finite lifespan. They do wear when they're written. And with this particular drive, with this particular metric, we get about 783 billion IOs before we reach that TBW value. Which then sort of begs the next question, well, what about cost? Aren't SSDs they're frightfully expensive? I'm sorry, Matt, did you?
No, I was agreeing with you. Oh, man, they're expensive.
Oh, yeah, okay. Well, it's a good question. So let's there's a tough call here, because we look at what it costs to buy an SSD versus what it costs to buy a hard drive, and yeah, there's often a big difference. And that's one metric. That's one valid way of looking at it. Acquisition cost is a valid way of looking at it. But once we buy it, then what? Well, once we buy it, we're going to do something with it, and we want that storage device to be reading, writing data as quickly as possible. And in fact, we can measure the value of it by looking at how much we paid versus what we got. So to figure out how those numbers shake out, Matt and I went shopping. We went out to Frugal back on the 15th, and we went shopping for a couple drives. We went shopping for that 600 gig 15K SAS drive, hard drive, and we took an average of 3 of the top prices. We really threw out the super expensive ones. We threw out the super cheap ones, the refurbs, the rebuilds, the no warranties, and we came up with an average of about $256 to buy that 600 gig hard drive. And, fair warning, your mileage may vary. Prices are probably different tomorrow. So this was a snapshot of one day of 3 seemingly average prices. And we did the same thing for our M500 DC 480 gig. And we came up with, on the SSD, $413.65. So the cost to buy one drive, $256 for the hard drive, $413 for the SSD. So that's the acquisition cost. Now let's take a look at what it actually gives us for what we spend. Let's talk about how much actual value we get out of this. And simply, we're going to look at the useful work, which we talked about was I/O operations per second. We're going to look at the price, and then we're going to do some more simple arithmetic. We're going to divide useful work by price, and that's really going to tell us what we paid for each unit of work. It's a really fair expression of value. And what we're looking at here is value. So this matrix, if you look at it a little closely, you'll notice it's slightly different. This matrix is a relative comparison where we show the performance of the SSD versus performance of the hard drive. And what we're looking at here is we've already factored in price. So this is a relative value expression. So it's performance by price as a ratio between these two devices. And the way that we've got this set up is if a given cell is green, that means the M500 DC gives a better value than the hard drive. If a given cell is red, it means the hard drive gives a better value than the SSD. And remember, we're factoring in cost. That's why this is a value expression, not a performance expression. If the cell is yellow, it's kind of a toss-up. It's within a few percentage points. We just wanted to call those out so you can see that there are some cases where, it's a little better, one's a little better than the other. So if we look at just making the raw comparison, we see that with the exception of the bottom left, the chart's all green. And remember that when the cells are all green, it means the SSD is a better value. We get more useful work per dollar paid from the SSD than we do from the hard drive, even though the hard drive is cheaper to buy. So really the hard drive is only showing better value in one spot, and even then it's only 1.1%. So that's an extremely large transfer with 100% rights. So we saw that at full purchase price, the SSD gives a better value, work performed per dollar spent, than the hard drive. So how cheap does the hard drive have to be in order for it to be a better value? And the way that we're going to know that, remember I said earlier, chart is that cell is green, SSD is a better value. Cell is red, hard drive is a better value. So what if we took the price from Frugal for the hard drive and we cut it in half? Now we're going to leave the SSD price exactly the same. So we took the price that we found, we cut it in half, and we said, well, what's the value comparison if the hard drive only costs us $128? And you can see when we cut the price of the hard drive in half, keep the SSD price exactly the same, that bottom row turns red. So we've got one row where the hard drive is actually a better value now. But remember, we cut its price in half in order to get there. Well, since the SSD still shows the vast majority of the cells green, it means it's still a better value. What happens if we cut the hard drive price in half again? So now we've gone from when we saw that $256 purchase price. Now we're saying, well, what would happen if we could buy that hard drive, that same hard drive, for $64? And then we compare how much value each one delivers. And you can see a few more cells turn red. So now when we get that hard drive for $64, it's showing it has a little bit more value, but most of the chart is still green. So let's keep going. Let's keep cutting the cost of the hard drive until we figure out how much it has to cost for the hard drive to give a better value. What if the hard drive was $30? Not $256. What if we could buy it brand new for $30? A few more cells turn red, a couple cells turn yellow, but still more than half of this matrix is green, showing the SSD is still a better value. What if it was $12? What if I could buy that 600 gig 15K RPM drive for $12? It's good, but we're still not there. We still have some areas where the SSD does better. Okay, what if I could buy it for $8? Nope, still have some green cells. Okay, what if we could buy that 600 gig 15K RPM hard drive for $2.60? And bingo, that's the right number. So in order for the hard drive to show better value, which is shown by all the cells turning red, we'd have to buy that hard drive for $2.60. At a purchase price of $2.60 for a 600 gig 15K RPM SAS hard drive, our M500 DC is no longer the better value.
But even at that, that means you have to buy a whole bunch of those hard drives to get that same performance.
Oh, heavens, yes. So that's an important point, thanks. So what we were looking at there is just the overall what we get versus what we spend ratio. So we took the performance of the SSD divided by its cost and took that quotient and divided it by the spin drive divided by its cost. But you're right. Our hard drive, we know it's still slower. Remember, it only does 470-something IOs at that 8K read 2, write 1, whereas our M500 DC does 22,000 plus. And, that kind of leads into the next point, Matt. You're a great straight man. So if we can buy that hard drive brand new for $2.60, it's clearly a better value as we've defined value. But from a performance perspective, how long would it take in order for us to realize that value? So it's kind of a polling question to the audience. How long do I have to use that SAS hard drive to get the same number of input-output operations the SSD can do? Remember, the SSD does 783 billion when it reaches TBW. So how long do I have to run the hard drive to get 753 billion IOs?
Okay, so instead of having to do the math, we'll give you three options. Will it take 5 years, 15 years, or 50 years?
So how long do I have to run that hard drive 24 hours a day, 7 days a week with that same IO pattern in order for the hard drive to execute the total number of IOs that my SSD does? And we'll give a second here. Do I need to vote on this, Matt?
I don't think so, no.
Okay. Well, you want to give it a minute and then? Yes, I do. I need to submit.
Are you going to vote too?
I don't know. Can you pull the results?
We got we'll go a couple more guesses. Come on.
Okay. I'm curious what folks on the phone think.
Okay. Well, only about a third of the audience is brave enough to even take a guess.
That's all right. Go ahead and pull it up. Let's see what we came up with.
So the audience at this point
looks like we've got most people thinking 50 years.
Yep, we're 2-1, yeah.
And the answer is you're correct. It's 52 years. You'd have to run that SSD the hard drive for 52 years to get the same total number of IOs out of it. So that begs the next. Yeah, there you go. Thanks, Matt. So I'm pretty sure most of the folks on the phone with a platform refresh cycle, it's shorter than 52 years. So what that really amounts to is when you're using that SAS rotating drive, you'll end up never getting the same value out of it as you would out of the M500 DC, executing that same metric. Okay, so click through that. Okay. What happens to our M500 DC SSD when it reaches TBW? So TBW is a specification that accompanies every solid-state drive that says how much data you can write through the interface before the drive goes into a read-only mode. It's typically subject to warranty from the manufacturer, and it's typically present in the data sheet. This is a standard way of measuring how many writes an SSD can accept. Matt, did we set this one up as a polling question? I don't think so.
No.
Okay, so the quick answer is the SSD becomes read-only. Your data doesn't actually go anywhere. When it reaches TBW, your data's still there. The data's still readable. All it is it's read-only. So because the SSD knows that it's reached TBW, it will typically disallow any additional writes. So that's why we call it read-only mode. How do you know when your SSD is worn, when it's essentially reached TBW or as it is reaching TBW? And the short answer there is it's going to tell you. So if we're looking at a SATA drive, like we are in the case of this M500 DC, typically they inform the host via smart. There's typically a smart attribute called percentage of lifetime used or percentage of lifetime remaining. It's different from different manufacturers. It's like a gas gauge. If you read that smart ID, it should report back a number, which is just like the gas gauge in your car. If the SSD's seen very little wear, it's going to be near or full. And if it's approaching TBW, it's going to be nearing being empty. SAS does it as well. SAS typically does it through a log page that you can also query. PCI Express, if it's an HCI derivative, it'll also use smart. Some NVMe devices use smart. But the point here is the SSD will tell you how close to TBW it is through standard means and monitoring. All you have to do when it approaches TBW, you copy the data off, replace it, put your data back, and go for another 783 billion IOs. So one key takeaway here, there's a couple. One of them is SSDs actually have a longer practical life than hard drives. If we take a look back at our platform refresh cycle options, and let's say we picked the longest one that was available, which was about 5 years, we saw that using a standard method of measuring performance or output operations per second, we saw that our really fast enterprise-grade hard drive can do about 75 billion IOs in those 5 years. And we also saw that our SSD, our M500 DC 480 gig, can do about 783 billion IOs in those same 5 years. So if I do the arithmetic, that looks like about, 10.5 times the total useful work output. So if we look at practical life in terms of the useful work output a device will do, clearly the SSD has a much longer practical life. And to do the arithmetic the other way, to look at how long we would have to have that hard drive in service, we'd have to run it for 52 years to do the same total amount of useful work that our SSD did. A key differentiator is predictable lifespan. SSDs have a very predictable lifespan, which lets us plan for replacements. It lets us schedule any necessary downtime for replacement. It lets us schedule a snapshot of an active data set to park that on an archive while we replace the SSDs that are worn, and then we put the data back. Ultimately, none of this is directly tied to NAND cycle count anymore. And I want to emphasize that because it used to be, back when I first got started with SSDs in early '08, we worried a lot about how many PE cycles on the NAND. And we've really evolved from then by having additional firmware enhancement techniques and acceleration hardware and controllers where at the SSD perspective, we can get more useful life out of the NAND in the SSD than we could the raw NAND. So the idea of TBW being directly tied to NAND cycle count, it just doesn't hold true anymore, and it really hasn't for a couple generations. SSDs report how worn they are through standard reporting mechanisms, and we can use these to ensure that we never get caught by surprise with a drive reaching TBW. We can, like I was saying earlier, plan for our replacements, plan to create our snapshots of active data sets, plan to place those back once replaced. We can schedule all of that because all of the SSDs tell us as they reach TBW. And the last thing to note is just because the SSD reaches TBW does not mean that the data is unavailable. In fact, just the opposite. When it reaches TBW, it goes into read-only mode. So you can read the data off of it, you just can't write more to it. We started talking about the end of life of Server 2003 and some of the concerns around the platforms that it was running on from back then. And what we ended up with was there's at least two distinct ways that we can handle that. The first way is we can upgrade. If we find that our hardware platform is able to be upgraded and support the minimum system requirements around Server 2012, this is a very good option for us. It's a money-saving option. It's an eco-friendly option. It enables us to recycle the vast majority of what's in that platform, make a few upgrades, and then move to a newer operating system like Server 2012. We can repurpose those platforms into other tasks and other workloads if they're not quite up to our frontline applications, but we can repurpose them. We can reuse them with these minor upgrades. One of the upgrades that we really want to look at if we're going down this route is using SSD to replace the rotating drives in those systems. And the reason for that is if we're doing the upgrade option, we're clearly interested in lifespan extension. And because the SSD has a much longer useful life than the hard drive, this is the better choice for us. Likewise, the value is very predictable and very measurable. The SSD will tell us as it approaches wear, so the management becomes much, much easier. But we did have another option. If we have a platform that just isn't capable of being upgraded, or it's so antiquated that we do need to retire it, or it's just time to start over with something fresher, we can do that too. This is a good path if we can't do those upgrades. But when we're considering the buy new path, we still need to be looking at SSDs as our storage devices. And that's really based on the idea of this useful work output, measuring useful work. And we saw that when we compare to a very fast enterprise-grade hard drive, the useful work output from the M500DC SSD eclipses the useful work output from the hard drive. And remember, if we're looking at overall value, going back to those cost comparisons, looking at the prices that we found on 515 for each of the devices, that hard drive would have to sell at retail for $2.60 to offer more value than the M500DC does. At this point, Matt, we can open it up to a bit of Q&A. Before we take off on that, there's a couple live links here that maybe some additional resources you might want to take a look at. There's a Server 2003 migration planning website. There's also some crucial upgrade advisor. There's also one out on Spiceworks. Take a look at our storage solutions page. There may be some key information there about any sort of upgrades or migrations you're planning. And then finally, there's a note there for the Enterprise MVP Elite program. So at this point, Matt, I think there may be one or two questions in the queue. I think.
Yeah, actually, I have a couple questions. First question up actually is about the SSD suppliers. Do all of the different SSD suppliers report to the SNIA, SNIA testing and measurement?
That's a good question. So do all SSD suppliers test their product in accordance with the PTSE?
Yes, and report to that too.
Oh, yeah. So there is a report. Let's do reporting first. There is a reporting function, but Micron's member of SNIA, full disclosure. I help write the Performance Test Spec Enterprise, full disclosure. The idea of reporting and publishing hasn't really garnered the level of interest and attraction that those of us in the SNIA Technical Working Group had initially hoped it would. So there may be some data out there, but I'd say typically SSD suppliers typically don't record the data measured on a PTSE in accordance, a reference test platform measured in accordance with that spec, typically don't report it. If there is stuff published out there, it's probably sporadic. It's not kept updated as firmware changes. The other comment I'd want to make is that that's one reporting mechanism, but there's another place that you don't see it, and that's data sheets. So if we look at enterprise and client SSD data sheets, including our own, we typically don't report all 56 points of the SNIA Performance Test Spec Enterprise Test Matrix. One reason for that, there has to be impetus to do it, and really demand from the customer base is one of the things that's going to help drive that. What you'll typically see in data sheets instead are either all read, all write measurements for small block and large block, just to give kind of four corners of performance. But you really don't see the PTSE IOPS test output in anybody's data sheet.
So like a typical performance, like you said, for an 8K bit 6535 workload type of activity.
Yeah, you probably would not see that in most SSD data sheets. What instead you would see would be like a 4K placement size with 100% read or 100% write, and that's going to show very high IOP numbers, very high IO operation per second numbers. And then if you look at the other metric you'll typically see is a large block sequential transfer, so typically 128K or so laid down sequentially, all read or all write. And the reason that number's in most data sheets is it ends up being a really big number. It's kind of a bragging value. And so you're going to see very large numbers there. What you don't see in data sheets is a more of a broader spectrum of measurement numbers. And like I said, it's really just response to customer demand. There is this standard out there. It's been adopted by multiple companies. There's data available a little bit on SNIA website. But at the end of the day, it'll be a response to customer demand that ends up getting into data sheets and more public-facing material. But just to be clear, the Performance Test Spec Enterprise, and by the way, you can download it for free. You don't even have to be a member. If you go to SNIA.org and search for PTSE, you can download a PDF copy of it that shows everything you wanted to know about how the mechanism behind the data that you and I showed, Matt, works. It shows pseudocode, so you can code it yourself if you want. There's commercial products available that will do the testing for you. There's even test houses that will test for you. But the one place you're really not seeing it is in a lot of data sheet or other customer-facing material.
Gotcha.
I'm not sure that answered the question or not.
No, that helped. Actually, I have another question here. What impact, if any, would the processor speed or DRAM capacity have on the life cycle expectations of a hard drive or an SSD?
It's a very good question. The answer, of course, is it depends. So in terms of hard drive life cycle, the thing that is really hard on hard drives, this is from studies I've read, data that I've seen, is spin up and spin down. So if we tend to spin our hard drives up and spin them down frequently, they tend not to last as long. And neither of those actions are really related to the specs just noted. So let's talk about SSDs. We have to remember first that an SSD wears when it's written, not when it's read. We should also be aware, and this might be a good topic for another webinar, Matt, different patterns and different transfer sizes will cause more or less wear. But at the end of the day, SSDs are warranted for the amount of data written through the interface, no matter how it's written. I want to be clear on that. If we have an SSD and the data sheet says that the TBW value is, I'm going to make something up here, 10 terabytes. Say it's 10 terabytes. Most data sheets will say that that's however you wrote it through the interface. That may be changing, where it may be a different TBW based on how the data is written, and the reason for that is smaller transfers tend to cause more wear than large transfers. And I'm getting around to the answer, I really am. Random placements cause more wear than sequential placements. So let's say we have a system that has a lot of DRAM, and let's say that system is writing data in very small sequential transfers. So for example, a logging system would be writing little small snippets of data completely sequentially because it's a time function. If we had a system that had a lot of DRAM, we may be able to gather up those small writes into DRAM and place them on the SSD as one large write. That would cause less wear than a bunch of little small writes. But that's only true when the data is sequential. If the data is placed randomly, that idea of gathering up or caching or concatenating before writing doesn't help us. And we could do a separate webinar on that, but the reason why is if the data is initially laid down randomly, even if it's concatenated in DRAM, that means that this host is going to delete data randomly or mark data as available for deletion randomly, which then gets rid of our sequential pattern. And there's a white paper on Micron.com on that one as well, Matt.
Yeah.
If anybody's interested, there's a contact info. I'm sure you can reach out to any of the MVP team members, and we can find you that white paper. But it does discuss the effect of transfer sizes and transfer patterns on SSD.
That makes sense. Yeah, it's like putting stuff in your garage. If you put it in a much more orderly fashion, then it's less wear on you. If you put it in a random fashion, then it wears you out more to get it.
Yeah, especially when you have to go in and find something in the garage.
Exactly.
And that's my problem. I can never find it.
So do you think we're ever get approach a time when hard drives will be designed out of enterprise servers?
Oh, I don't know. I'm always reluctant to predict the future. It's fraught with peril. I can tell you that if we took a snapshot today, hard drives, I mean, they still have a place. It's not the place they used to occupy, but they still have a place. if you look at just raw capacity that's on the open market today, you can get a 3.5-inch helium-filled rotating drive. It's like 4 terabytes, 8 terabytes. I mean, it's painfully slow. That's why we didn't use it in this example. It's painfully slow to use, but you can do it. And you get a lot of storage density. Storage density has always been the argument for hard drives. If we have a 1U 4-spindle system, we get 32 terabytes in RAID 0 and 1U. That's really good. But that's about the end of what's good about it. Will they ever go away? Gosh, I don't know. But I do think what you'll see is as more SSDs are built to specific workloads or tuned to specific environmental requirements, you're going to see more and more a wider proliferation of different SSD types, which will then occupy those sockets that hard drives used to occupy. For example, if we look at booting up a system, typically some platform vendors will ship a 15,000 RPM SAS drive pair in hardware RAID 1 as a boot array for an enterprise platform. That's a pretty common practice. They want small hard drives because it's just an operating system and maybe a few apps. If we look at SSDs, I mean, there's a lot of advantages to even booting a system off SSD. But even if you took the same configuration, 2 drives, you put them in RAID 1, with a product that's on the market today, we're approaching very similar pricing in per usable gigabyte. That's a very light workload, so we don't need the extra endurance of a higher-end SSD for it, and consequently the price drops. So will we ever get there? I don't know. Like I said, it's tough to predict the future, but I will go out and say that as these wider variety of SSDs get designed for specific workloads, their proliferation will increase, and I think you'll see the proliferation of hard drives decrease to where eventually it just becomes a capacity play.
So I think you can safely say SSDs are not just a fad.
Oh yeah, I mean that's for certain. If I wind back the clock, like I was mentioned earlier, back to '08 when I first started looking at these things, they had very, very specific narrow uses. Now, in just these few short years, 7 years later, we have SSDs everywhere from in our mobile systems to little ones that are the size of a postage stamp that boot up tablets and hold all the tablet data. We've got incredibly fast dual-port SAS SSDs that eclipse the rotating drive performance, sometimes dozens and dozens of rotating drive performance. Those are making their way into arrays. We've got inside of servers, we have local storage for the same reason. It just eclipses the overall value the hard drive brings. So a fad? No, definitely not a fad.
Great. Well, Doug, thank you for your insight. I think this was a very helpful webinar. And again, people still in the audience, if you want to provide some feedback, either online through some of the feedback channels. We do have our next webinar coming up is in next month. Our June webinar is June 15th. It is with Rob Peglar, our Vice President of Advanced Storage Solutions, and he'll be talking about big data, advanced storage, and other fun stuff. So that should be entertaining and very informative. And also, before we go, I do want to thank everyone for registering and participating in the attending the webinar. We will have a drawing, so 3 lucky recipients are going to win a 250 gigabyte Crucial SSD, courtesy of Micron. So again, thank you all for participating, and hope to see you on June 15th for our Big Data webinar. Thanks,
everybody. Appreciate your time.
Thanks, Doug.
You bet.